Thanks for the nice introduction, Fadil. I really appreciate it. So the original plan for this talk was to talk about spatial AI for everyday robotics, but these things go. So on the flight here, there were some changes. I guess I'm going to make the title maybe a little bit more aligned with the topic of the workshop. So I'm going to talk about reliable and trustworthy robot perception. So small change in the title to focus a little bit more on robustness and trustworthiness. So we have 30 minutes or so together here. My plan was to cover 3 main areas of work. These are fairly different lines of work. Some are about mapping, some are about object understanding instead, but there is a common underpinning of talking about robustness, how to make things work in the real world. So the 3 pieces of the talk, I'm going to start talking about Hydra and 3D scene graphs. That has been a big topic in my group for a while. Many of you have scene graphs, have seen work in 3D scene graphs. I'm going to tell you about the tricks we are doing to make the semantic understanding underlying 3D scene graphs a little bit more robust using neurosymbolic reasoning. In the second part of the talk, I'm going to take a different perspective on robustness. I'm going to talk about robustness in dynamic environments. And the final part will conclude with a different topic, which is about object understanding. Of course, object understanding is important for mapping as well, but I'm going to zoom in on estimating pose and shape of objects, and I'm telling you what are the challenges in getting that right, in getting that to be a robust technology. Okay. So let me start and work on 3D construction. We've been big proponents of 3D scene graphs as a representation for robotics. I'm a single in this audience. Representation is a rich map representation, which is hierarchically linear. So what you see here is a scene graph. Essentially, there are different layers. At the lowest layer, you have dense information about geometry. That's a traditional map, mesh, if you want. But as you go up in the layers, you get to abstract away information, and you get a more abstract representation, including layer 2 with object and agents. Layer 3 structure places are essentially like a traversability map of the environment. And for indoor environments, you get to layer 4 of rooms, buildings, and so on. So in a nutshell, a scene graph is a hierarchical representation. It's essentially a graph in which nodes are spatial concepts, anything that lives in 3D. And edges are about relations within these concepts. For example, an edge cutting from an object to the mesh, saying that the specific object is grounded on a specific portion of the mesh. Or, I don't know, an edge connecting 2 rooms means that, the 2 rooms are nearby, they share a door, they're accessible from one to the other. So over the last several years, we spent time, not only defining scene graphs, but also building real-time methods to construct scene graphs. Many of you have seen Hydra, which is the most recent system we have to build the scene graphs. In a nutshell, Hydra, you can think about this as the evolution of SLAM, simultaneous localization and mapping, in which the robot is prior knowledge about the environment, is building these scene graphs in real time. So in this example, I'm going to play the robot is starting in a kitchen environment without any prior knowledge. The robot is moving around, is building a 3D mesh, and is ignore the fact that if a room contains maybe a fridge, a table, likely that room is in rather than a bedroom, for example. So I will not tell you too much about Hydra. I will zoom in on a specific aspect, which is what I have in the next slides. But I want to share that essentially these techniques are a cool mix of traditional SLAM, traditional geometric reasoning, and new tools from deep learning. For example, everything about the mesh construction is just traditional 3D construction. But then on top of that, we have a transformer-based architecture, which is doing the semantic understanding in the image. And then we even have a graph neural network, which is taking the objects in the room and predicting the label for the room itself. So rather than talking about these, I want to talk about more recent extension of this work on scene graph to outdoor environments. The idea of hierarchy extends fairly nicely to outdoor environments, as we have a hierarchy of rooms, floors, buildings, and so on in indoor. We can have the same level of hierarchy in outdoor. For example, in outdoor, we still have, of course, a dense mesh representation. That's pretty much like our dense map of the environments. Of course, we'll have still notion of objects, and of course, we still have a notion of places. Again, these are the locations that are traversable by the robot, so we can define these in outdoor as well. The thing that is a bit different is that in outdoor environments, of course, the top layers the top layers might be a little bit different. Instead of caring about rooms, buildings, and so on, in outdoor, you might care about roads, fields, park, like different type of concepts. So the question that we really look into is how to classify places, how to figure out these top layers of the scene graph, how to classify places, which are this graph in black, into high-level regions, for example, road, field, and so on. So how to build, again, like, the top layers of the scene graph. It's kind of a challenging problem, and the main challenge here is that there is a lack of training environments, which might sound a little bit funny because we have things like, Google Street View and so on. But actually, the data we need is data correlating objects in the scene with the name of the region they're in. For example, saying that a bunch of trees are in a forest, or traffic lights might be at an intersection in an urban environment, right? So that data is still not available in training data sets. And that's very different from indoor, in which you have plenty of training data sets. So therefore, we said, without training data, without data, how do we increase the robustness of classification of these regions? How do we populate these top layers of the scene graph? And we went back to an idea, again, that is about neurosymbolic. I will unpack the different aspects like in this slide. But the basic idea is to use an ontology. An ontology is kind of a graph design, what are the allowed relations between concepts in your scene graph. For example, this ontology is saying that for a room, we classify it as a bedroom, as a kitchen, you want a fridge, a sink. So essentially, it's establishing through the links in this graph what are the relations that you expect to find. And this, of course, will help you classify the regions, right? You can see a bed, a wardrobe, and so on, classify that region as a bedroom in this case. So the idea of ontology goes back many years ago. It's a very traditional idea of classical AI. We have put this here, this thing. First of all, the idea of ontology is that it's not practical for a human just to write down this graph. This graph can be potentially very large. We don't want to do saying what are the key objects from the labels, which are the most likely to distinguish, I don't know, a bedroom from a bathroom, or like a bedroom from all the other rooms. And by acquiring multiple happens all the time. You can think about the ontology as a set of predicates. For example, an engine ontology can say that the room is a kitchen if there is a chair within it. So what we do is we use a tool from neurosymbolic, which is called a logic tensor network, which is just a way to train a neural network, a way to maximize the satisfaction on a number of predicates. Sounds a little bit complicated. Actually, the question is designing a way that is maximizing the satisfaction of these predicates. Okay, so the only thing that we really do is take a neural network and we design a loss function, which is as a nature which is closer to logic rather than cross entropy or the other cost functions that you typically find in deep learning. Okay. Just as a summary, with the large language models, we build an ontology, and then at training time, we use the ontology to enforce specific relations in our predictions. And of course, in Notion, you can have both. You can both enforce the ontology, but you can use also data-driven terms, right? You can do both. You can do essentially traditional deep learning, but you can also allow or enforce this satisfaction of the logical predicates that you have. This turns out to be working pretty well. So we can have a combination of these predicates and ontology with the terms. What I'm going to show you is a small-scale experiment. I'm going to show you a much larger one in a couple of slides. Essentially, you can show a small-scale experiment in which the starts with operating environment, is driving around, using this. So detecting objects, I don't know, in this case, there is a tree there and so on. And then these places that you see at the top will get classified into different regions of the map. Okay. And you can see a little bit of the details of the mesh reconstruction. I think you can do a better job, to be honest, at reconstructing the mesh but right now, like, this is working pretty well, and it's very lightweight. All of this is running in real time on robots at this point. Okay, so maybe one slide about quantitative results. Turns out that this idea of the LTN or logic tensor network is pretty good in practice, and in particular improves the performance of your prediction. You can apply this to any source of network. We apply that to a graph neural network, but essentially in the presence of the low data regime, which do not have lots of training data, using this logic tensor network is making the predictions much better, because again, you set a bunch of predicates, a bunch of rules that you want the prediction to satisfy. So just to unpack, first of all, we do large-scale testing at West Point and Castle Island, which is like, close to MIT. If you look at the numerical results, this is kind of accuracy of the classification. For example, if you say that a place is an off-road or a walk, if you get it right, that's like, we measure essentially the fraction of labels for which we get, fraction of places for which we get the label right. And what you see in the columns, most column is the case in which you have very little training data, you have to still do a good job. And I'm comparing a traditional cross-entropy type of supervision with just data-driven terms. What happens is that the cross-entropy is doing great enough training data, but as you get less and less training data, the accuracy, the percentage accuracy really drops to close to random chance, like, the 12% is close to random chance. And instead, the approach in green, where SAT stands for satisfaction, I don't know why we didn't call it LTN, but essentially the approach that we propose at the bottom, first of all, when lots of training data, because we use the ontology, we get better performance, but also when you have more clever about exchanging information in multi-robot systems. We can do motion prediction. I think that paper is going to be presented at ICRA. And then, it says archive is actually Ralph is going to be presented at ICRA. And then the paper at the bottom are doing task planning, goal navigation, manipulation, and so on. So as a representation, is pretty powerful to support all these tasks. So far, I told you about how to get, with this idea of neurosymbolic reasoning, how to get a little bit better accuracy in predicting the semantics or classifying the places in the scene graph. Next, I'm going to tell you about robustness to dynamic environments. Okay, I'm going to talk about dynamic environments and changing environments. And I'm going to describe Chronos, which is a paper that we presented at RSS last year, which is essentially getting towards 3D scene graph construction in which you have dynamic, getting with very dynamic. I'm not going to present 3D scene graph per se, it's going to be more of a SLAM representation, but we are getting there. So with this audience, I don't know if I have to spend lots of time motivating the need for dynamic environments. But, if you end up doing real experiments with robots, like all sorts of experiments, you realize that robotics is what we call a temporal mapping approach. Makes semantic because we're going to build meshes for which we can easily information in the paper. Itself will contain information and so on, but also spatial changes and to reason over change bar short term synchronous within the field of view of the camera, as well as do what is called change detection to reason over long-term changes which have happened while the robot was not seen. Is a full representation in the sense that not only we're going to estimate the state of the objects at the current time, problem and increase the object fragments. Then we can factorize if we can factorize this problem in a much easier way. So we try to unpack this a little bit. Let me play with that. And these pieces, these fragments are such that they are observed over a short amount of time where is negligible. That's the basic idea. Like, fragment is a portion of object which is observed over a short enough time that the geometry noise is not a problem. So including this idea of objects, you add that very regional optimization problem in 3 parts. The 3 parts, I will not look into. After you estimate the fragments, you have to globally optimize for the position of these fragments and try to reconstruct objects from the fragments, which is the SLAM part. Essentially, we show that the piece here, which is the SLAM part, we have to solve some robust SLAM problem in which we have to associate fragments to specific objects. And then the last term is about just like, after I solve the SLAM problem, I have to put together fragments together, like, and define an object, for example, the gray box in my, like, figure at the bottom here. Okay, so some factorization of the belief, and this is cool because it will suggest kind of a split OR implementation in which the rightmost will be kind of a voxel-based reconstruction that we perform locally, and that is decoupled from the SLAM backend, which is the middle term here. So we can do a clever implementation to work on this factorization and solve the inference problem in a better way. On top of that, so that part was more about reasoning over objects and reconstructing objects. We do some clever reasoning about long-term changes, and I'm going to play this video just to give a sense of what we do. First of all, we try to reconstruct the entire history of objects. We don't just say that an object is present at a given time. We want to figure out the entire history where the object was, or when it was present or not. So this video is showing a little bit the reasoning that goes into Chronos. Essentially, if you detect the object at the initial time, you say, okay, the object is present. If you detect it at a later time, you infer that the object has been there for all the time. If later on, maybe we don't detect the object, but the depth measurements that we take are still consistent with our estimate of the position of the object, we still confirm that the object was there. If at some point our depth measurements are showing that the depth we measure is not consistent with our object estimate, we infer that the object disappeared, and we do some inference over the time at which it disappeared. Okay, so what you see here, essentially the axis is time, and we can trace exactly where the object appeared and where the object disappeared. That's the 4D understanding that Chronos is able to do. So let me close with a couple of I want to move to the last part. Let me close with a couple of real experiments. This is an experiment at MIT. For a lot of the things we do, we put a lot of effort in keeping the code to run on real robots, but also to run to be quite lightweight. Chronos still needs some work for scalability, but at this point we have a version which is public, it's open source, is running on CPU, and this is the one we use to get the experiments at MIT. So here what's going on is that the robot is starting at the bottom. There is a large room, this building 31 at MIT, then he's driving through some corridor, and is going around. In the meanwhile, Lucas, who is the first author on this paper, is rearranging the objects in the room at the bottom. So what you see is that Chronos will keep estimating the trajectory. At some point, there is some person moving in front of the camera. Yes, that's Lucas again, probably. And we'll be able to track the motion of person. But also when it's coming back to the room where Lucas, the red disappeared, that's probably the chair that disappeared. And we'll also see that the water cooler is not there. So hopefully another red box will pop up there. Actually, the cooler was added, so that's why it's green. Something was added and something was removed. Okay, lots of numerical results here. I don't know if I want to get into the merit of the numbers here. Essentially, for this kind of systems, you care about several things. You care about the quality of the 3D reconstruction of the background. Not only you care about the objects, but you want to mesh the goods. You care about being able to understand the objects themselves. You care about tracking short-term dynamics, and you care about doing a good job at long-term change detection. So here for the background, I think all the approaches are doing well. Some of the approaches have troubles because they don't account properly for the dynamics. And the ones in yellow have a little bit lower precision or lower recall, but all the approaches are decent, I would say. when it comes to the object, like most of the approaches are okay. The part where Chronos shines really is the part regarding the dynamics, in particular, on the type of tracking that we do for the short-term dynamics seems to be much more effective than approaches like Dynablocks, panoptic mapping, high-resilience static environments, so there is not much we can do there. And we are doing okay on the change detection. If you look at the numbers, we are still the best performing, but the absolute number, which are kind of precision recall numbers, they're fairly low. Like for these numbers to be 100%, they're fairly low, which essentially means that change detection is still a tough problem. There's some solution, but there is a lot to improve here. Okay, so the last experiment we spot, we've done a lot of real-world experiments, but we skip that, and maybe in the last 5-6 minutes, I will move to the last part of the presentation. So the last part of the presentation is still about robustness, but it's about object understanding. So there is a little bit of a switch here. So far, I've been talking mostly about mapping. Now I want to tell you about how to understand objects. Of course, these are not two orthogonal directions. Of course, we can map objects in the scene, so they're not completely different. But you see that the technical tools are slightly different here. This, by the way, what I'm going to present is called CRISP, which is a paper that's going to be presented at CVPR next month in Nashville. So what do we want to do here? The basic idea is to use RGB data to do object pose and shape estimation. Okay, so you give me camera data. I want to figure out what is the pose of the object. I want to figure out the reconstruction of the shape of the object itself. So the typical approach to this that you will see in deep learning is that we have input data in, we do some neural network, and we get an estimate out. For example, the estimate can be something like an SDF, or can be any representation that you want. Lots of work in this area. At CVPR, there will be there have been hundreds of papers over the last several years, considering this type of problems. The issue you see in robotics is that, where you deploy, whenever you deploy the robot, you will see that things are different from your training distribution, and nothing will work as well as when you test things on data set, right? So the real robots, reality check these kind of approaches. And indeed, what happens, and the reason why we started working on this is that on data sets, everything works beautifully. Many of you might be familiar with the YCB data set MAG on the left. So if an object is from the data set, everything will work great. But if you start changing a little bit the domain, you put a different MAG, a different object, use a well-trained network, and the result that you get is not as nice. Okay. So the observation is that there is a domain shift between the training distribution and the test distribution. In robotics, you're always going to see that. And because of that, the network, unless we get substantially better tools from deep learning, the network is going to be producing a bad result. So the question is, can we get some robustness to that? And in particular, can we do something that is called test time adaptation? We want my network to be tested offline, maybe on the YCB dataset, but then at test time, I want for the network to adapt and learn about the current environment. Okay, I want to get better predictions from it. So next, I will show you the architecture we use, which I think is very simple, to be honest. And then I will tell you a little bit of the contributions we have within this architecture. The idea should be pretty intuitive, but we do the same. We start with the same architecture, RGBD data, a neural network, and then a network estimate. We're going to do something a little bit more clever about the architecture of the network. Your network is something that we call CRISP. I'm going to tell you, if you're really into deep learning, I'm going to tell you the specific details about the architecture. But again, we don't expect this to work great. If it is out of distribution, the network is going to produce some estimate that is not going to be great. So what we propose is to do what is called a corrector. Essentially do a model-based optimization approach, which is refining the estimates from the neural network. To show essentially we're solving an optimization problem, and this in practice is fitting data and trying to compensate a little bit for the domain gap. But on top of that, we look at the final result, which is the MAG on the right-hand side, and we have a certifier. The certifier is going to be a very simple block, which is checking if the estimate is consistent with real data or not, if essentially the estimate is a plausible result or not. And what we do is that if the certifier gives us the green light, saying that the object estimate is pretty good, we add it to the training set. you are like into object understanding with deep learning, like shouldn't be too surprising. So what we do here, we take RGBD images and we segment out the specific object we care about. For example, we have an entire image and we segment out the mug from the image here. Then we pass the mask corresponding to the object to a RT backbone. We can have a dyno V2 doing that job for us. And then there are two heads. There is a head predicting the shape and a head predicting the pose. For the shape, is encoder-decoder network with the film preconditioning. You do not have to understand too much, but essentially there is an MLP which is producing, that's like the encoder, in an embedding vector, and then the embedding vector is decoded into an SDF, decoded into like a dense representation. And at the bottom, instead, there is some prediction for the pose, where we use some other transformer network, which is this dense prediction transformer, to essentially figure out the pose. We figure out the points in a normalized way, which is pretty much the same as estimating the pose of the object. I don't want to get into the choices. I guess they're well updated. A little bit more insight is the notion of corrector. Corrector again is just a model-based optimization approach, which is given the result of the network as a niche, as you can hear. And so what here, we are a little bit more clever about the optimization problem because we have a single observation, which I think is pretty interesting. The observation is the following. Imagine that at training time, you train your shape reconstruction, the encoder and decoder for your shape reconstruction on n different objects. So you have a lot of objects, but that define a set of objects. The basic observation is that you can interpolate very well objects in the convex hull of the objects you have seen. For example, if at training time you have seen a drill and you have seen a box, you can do a pretty good job at interpolating shapes between these two objects. But if you try to extrapolate, the results are a complete mess. Okay, so the basic idea here is that interpolation for the object shape will work very well, extrapolation not as much. Okay? So what we do indeed is to say, look, when you have to optimize and figure out the object shape, don't optimize everywhere, just optimize over the convex hull of the shapes you have seen. So constrain the optimization to the convex shape you have seen. Lots of technical details, but essentially what you optimize for is the vector embedding. Okay, so if I go back to the architecture, maybe like this guy, you see that for the shape is an H, which is the result of some encoder. We optimize that vector. Okay, and we keep the. Okay, so we optimize the embedding and we make sure that the embedding remains in the convex. If it's good or not. And whenever the certificate passes, again, I can use this as pseudo label and obviously it and keep it with my neural network. So a couple of slides and then I will close. These are like some results from the CVPR paper. The results are showing like quantitative results on the side. You can see the picture, and you can see the examples of the shape reconstructions. I mean, the quantitative results, I mean, the takeaway point, maybe if you look at the shapes are pretty crisp, pun intended, I guess. And like, there are pretty good reconstructions for all the objects, like in the images. There is a lot to unpack in the numerical results, because in the numerical results, we both validate the architecture in a supervised way, as well as show the value of the self-supervision. The top table is showing the accuracy of the shape reconstruction compared to Shape, which is a baseline, and the bottom one instead is evaluating the performance of the pose estimate. So essentially, if you do this in a pure supervised manner, you get the last row of the table. Everything is green, which means that we largely beat the state of the art. The middle rows are about saying if you start from a network which is trained in simulation and you just do self-supervised learning with the architecture I was showing, essentially the self-supervised learning gets results which are much better than the original data set. And they get not exactly they get pretty close to the fully supervised setting. And we have plenty of results with this. In this talk, I'm not showing that, but actually in the paper, I have the application just to show the robustness and heterogeneity of things. We have an application and demonstration on these data sets, which are more like indoor data sets, but we have a demonstration and satellite data set, which from data you have to reconstruct the shape of a satellite. So seems to generalize pretty well. With that, I will conclude with the last slide. So in this talk, I told you about robustness in robot perception. I started with robustness of building the top layers of the scene graph and reconstructing the semantics of the top layers of the scene, robustness to dynamic elements in the environments. And then with CRISP, that again is going to present a CVPR. I told you about test time adaptation and how to get robustness to shift in the domain distribution. And with that, I will close. I will thank our sponsors, and I will thank you for your attention as well.